Hi everybody, this is Professor Mankowski, and this is going to be video number 2 of our Introduction to Hypothesis Testing. In the first video, we found out a little bit more about what the hypothesis test process was about. We learned what sampling error was, and we found out that there's 5 different steps to the hypothesis test method. We also found out a little bit more about what the step 1 null and alternative hypothesis is, how to define the null hypothesis and the alternative hypothesis, and the 3 different variations, the left tail test, the right tail test, and the two-tail test, as well as how to recognize when we have which variation. What we're going to do in this video is we're going to take a look at a full-blown hypothesis test question, and we're going to practice steps 1 and steps 2. So let's go ahead and let's bring a question right up on the screen. Pause the video for a couple minutes if you need to read through. Okay, in this video, it seems that there is a inventor. They've made a new kind of fertilizer for peanut farming. And they happen to know that if you're a peanut farmer, your average yield is going to be about 3,000 pounds per acre. When they invent the fertilizer, then that means it has to beat 3,000 pounds per acre for it to sell. So what they do is they go out and they test the fertilizer on 60 individual plots of land or 60 farms. And they're going to need to show that the average yield they get on those 60 farms is greater than 3,000 pounds. When we look at the average yield, 3,120, it looks obviously like it's a larger number than 3,000. So can we just stop there and say it's proof that the fertilizer worked? Not so fast. And the reason why is we have to find out, is 3,120 significantly higher than 3,000 or not? If it isn't significantly higher than 3,000, that means it's not proof that the fertilizer actually did any good. Because if it's not significantly higher, it means that the difference between 3,120 and 3,000 is simply due to sampling error. Or in other words, the implication would be that a peanut farmer could get a yield of 3,120 pounds during a really good harvest on a good year without doing any special fertilizer. And if that's the case, if the difference is due to sampling error, then it means that we don't really have any way of attributing the higher yield to the fertilizer alone. So let's go ahead and let's start to record some of the key information we're going to need for the question. We're going to write down that our population average is equal to 3,000 pounds. And I just want to take a minute to talk about how we knew that the 3,000 was our mu, because this is an area where students get confused often. There's 2 averages specified in our question. The average production of peanuts is 3,000 pounds, and then they tell us later on that we have a mean yield that's 3,120 pounds. So how do you know which one is supposed to be your population average mu? And the fast answer is that 3,120 seems to be connected to the information they're giving us from the 60 plots of land. So 3,120 must belong to the sample, or refer to our X bar. So we're going to go ahead and we're going to fill in the rest of our numbers here and label them accordingly. And now let's think about step 1 of the hypothesis test. We're going to follow the same pattern that we had seen in the last video. We're going to take our null hypothesis and we're going to set it up where mu is equal to 3,000 pounds, the currently believed population average. For the alternative hypothesis, our key word is that we're looking for an increase. So we're going to create a right tail test, and we're going to specify that H1 would say mu is greater than 3,000 pounds. Now it's time for our critical values. We just need to know 2 things to find the critical values: the alpha of 0.05 and that we're doing a right tail test. But we're going to go ahead and we're going to sketch a curve. And one thing that we have to be really careful of, inside the question, we have a population standard deviation. So that means we're going to use the Z curve, not the T curve. Back to our curve then, what we're going to do is we're going to identify the top 5% of our curve, and we're going to go ahead and we're going to shade that region in. And then in our Z table, we're going to find the Z score that matches the most closely with the top 5% of our curve. And that Z area is going to be, or rather Z score is going to be 1.65. So 1.65 becomes our critical value. Now, what are we going to do with that 1.65 for a critical value? That's what we're going to find out in the next video, how to use it. Let's go ahead. Let's take a look at another practice case. Take a minute to pause through the video to read if you need to. Okay, so as we're working through the situation here, it looks like that if you're a federal government employee, you're going to be making on average $59,593. And somebody thinks that if you're a state employee and you do similar work compared to the federal employee, your salary is going to be less. And if that's true, that's telling you something important, because it means if you're a state employee, you probably want to think about switching over to the federal government, because for the same kind of work, you could be getting more money. So this person goes out to find out if they're correct. They sample 30 different employees, and they're going to look at the population. They're going to look at the sample average rather, and the sample average came out to be $58,800. And we need to figure out, is that significantly less than what the average federal employee makes? So let's start to write out our population average. We're going to write down that mu is equal to $59,593, and we're going to pencil in the rest of our numbers here. Okay, we're going to start to think about creating our hypotheses, null and alternative hypothesis. For the HO, same pattern as before, we're going to set mu equal to the population average, $59,593. For our alternative hypothesis, our key word is less than. That means we're going to set up for a left tail test. H1 will say that mu is less than $59,593. We're going to think next about our critical values. We know that our alpha is 0.01 and we have a left tail test. That means we're going to go on our curve and we're going to shade in the lowest 1% of our curve. We're going to go in our Z table and we're going to find out which Z score comes, which Z value rather comes the closest to 1% area in that curve. And that value is going to turn out to be negative 2.33. So we're going to write in that our critical value is equal to minus 2.33. Let's take a look at one more question. Pause the video again if you need to go ahead and read through. In here, they're telling us the average salary of a public school teacher is about $39,385. And perhaps a researcher has come up with the belief that in one particular region, the salary of teachers is less than that national average. And they go ahead and they do a sample of 50 school teachers from that area. And they want to find out if that salary is significantly different in that sample average from $39,385. So let's go ahead and let's write down that our population average is $39,385. We're going to pencil in all the other information that they gave us and put on the labels accordingly. For our alternative and our null hypotheses, we're going to set HO to read that mu is equal to $39,385. For our alternative hypothesis, because we noticed the keyword differs, we're going to set up for a two-tail test. And we're going to write down that mu is not equal to $39,385. Time for critical values. When we do a two-tail test, we have to do something a little special. Only when you have a two-tail test, we're going to take our alpha level and we're going to divide it by 2. We're going to use 0.05 and we're going to split that by 2. We're going to get 2.5% or 0.025. Going into our curve, we're going to set our shading up on the left side and the right side at the same time because we have a two-tail test. So we're going to take that 2.5% and we're going to shade the left area 2.5% and the right area 2.5%. Now we go to our Z tables and we're going to find out what's the Z score or the Z value that comes the closest with matching the lowest 2.5% area and the uppermost region of the highest 2.5% area on our curve. And those two numbers are going to be plus and minus 1.96, giving us our two critical values.